Even before the first shots of World War II rang across Europe and the Pacific, American industry faced a daunting reality. The nation was not prepared for the scale of aerial warfare that modern conflict demanded. Aircraft production was scattered, small-scale, and limited by peacetime priorities. The factories that existed produced planes in quantities suitable for ceremonial flyovers, airshows, or training, not for the relentless demands of global combat. Yet, as reports of the Luftwaffe's raids over Poland and France reached American ears, industrialists, engineers, and military leaders recognized that air power would define the outcome of the war. A decision was made. The United States would transform its economy and its factories into a war machine capable of producing planes faster, cheaper, and more efficiently than any power on Earth. The first challenge was scale. Aircraft that once took months to construct had to be produced in days without sacrificing quality. Engineers revisited every component, from engines to wing spars, from fuselage frames to landing gear, to simplify designs, standardize parts, and allow mass production. Factories that had once produced automobiles, refrigerators, and consumer goods were retrofitted to serve as assembly lines for aircraft. Assembly lines stretched for hundreds of feet, with workers specializing in a single task repeated thousands of times. The precision required was extraordinary. Even the slightest misalignment could spell disaster for a pilot in flight. Yet, the American industrial mindset, efficient, innovative, and relentless, rose to the occasion. Labor became another crucial element. Millions of workers, including women who had never before held positions in heavy industry, poured into aircraft factories. They were trained in welding, riveting, and assembly, learning to construct complex aircraft components with unprecedented speed. The Rosie the Riveter image became more than propaganda. It symbolized a workforce that had transformed itself overnight, sacrificing comfort, leisure, and personal safety for the survival of a nation. Factories hummed 24 hours a day, guided by foremen, engineers, and inspectors who ensured that every plane met exacting military standards. The U.S. government recognized that mass production required coordination on a scale never before attempted. Agencies like the War Production Board and the Office of Aircraft Production orchestrated the flow of raw materials, labor, and machinery. Aluminum, steel, rubber, and aviation fuel were rationed and redirected toward factories, while shipping networks delivered critical components to assembly plants across the country. This logistical orchestration became a war effort in itself, a silent engine behind the roaring propellers that would soon dominate the skies. Innovation played a central role. Engineers developed jigs, templates, and modular assembly techniques that allowed sections of planes to be constructed simultaneously in different facilities and then brought together for final assembly. Subcontractors, often producing seemingly minor components, became vital cogs in a massive industrial ecosystem. A single delay in the production of engines or propellers could halt the construction of hundreds of planes, so synchronization and foresight became as critical as steel and rivets. The scale of planning mirrored the complexity of a battlefield campaign, with deadlines, contingencies, and targets dictating the tempo of civilian and military life alike. Financial incentives fueled urgency. The U.S. government offered contracts that promised enormous profits, but only for manufacturers who could meet strict production quotas without sacrificing quality. Competition among companies, from Boeing to Lockheed to Douglas, pushed innovation and efficiency forward at a relentless pace. New plants sprang up in cities and rural areas alike, often in regions previously untouched by heavy industry. Workers were relocated, entire communities transformed, and entire supply chains reimagined. By the time America formally entered the war, the skeletal framework of a massive aircraft production network was already in motion. The human element of production was profound. Workers endured long shifts, repetitive labor, and dangerous conditions. Factories were loud, crowded, and hot, yet morale was bolstered by the knowledge that each rivet driven, each panel welded, and each engine tested was directly contributing to the survival of Allied forces abroad. Stories emerged of women and men working through the night to finish planes for missions over Europe or staying behind to repair critical parts for squadrons departing the next morning. Their labor was anonymous but essential, the hidden backbone of aerial dominance. By the end of 1941, before the attack on Pearl Harbor, the foundations of mass aircraft production were in place. The factories had been transformed, the workforce trained and mobilized, and the supply chain streamlined to a level never seen before in peacetime America. What had once seemed impossible, the rapid construction of thousands of complex warplanes, was now not just possible, but inevitable. And with the formal entry of the United States into World War II, this industrial might would be unleashed, reshaping the skies over Europe and the Pacific and setting the stage for an unprecedented display of American ingenuity, labor, and industrial power. With factories prepared and labor mobilized, the next monumental task was translating complex aircraft designs into production-ready models that could be built in large numbers without sacrificing quality. Engineers worked feverishly, transforming blueprints into standardized templates and modular sections. The P-51 Mustang, B-17 Flying Fortress, and later the B-29 Superfortress began as sketches and prototypes, but mass production required revolutionary thinking. Components that had once been handcrafted had to be engineered for replication, with tolerances that allowed sections built in different locations to fit together perfectly. This required a meticulous understanding of aerodynamics, materials science, and human ergonomics, as well as an unprecedented level of coordination between designers, suppliers, and assembly teams. The production of engines became one of the most complex challenges. High-performance aircraft engines contained thousands of parts, each requiring precision machining and rigorous testing. Pratt & Whitney, Wright, and Allison engines became lifelines for the air war, yet scaling their production demanded innovation at every stage. Manufacturing tolerances were tightened, assembly jigs were developed, and test benches simulated the stresses of combat before engines were cleared for installation. Engineers devised ways to produce multiple parts simultaneously, utilizing specialized machinery and assembly teams that became experts in a single component. Efficiency became a matter of life and death, as delays in engine production could stall entire squadrons. Raw materials were another constant obstacle. Aluminum, vital for fuselages and wings, was scarce and had to be allocated carefully. Steel, rubber, and copper faced similar pressures. Factories operated on rationing systems, carefully planning every sheet of metal, every pound of rivets, and every coil of wiring. The War Production Board coordinated shipments from mines and refineries across the country, ensuring that aircraft factories received a steady flow of materials despite competing demands from shipyards, tank plants, and other military industries. Logistics became a silent battlefield, fought in warehouses and rail yards, whose victories would ripple into the skies thousands of miles away. Labor itself required careful management. Millions of men and women, many with no prior experience in heavy industry, were trained in weeks, sometimes days, to perform specialized tasks. Riveters became experts in fastening aluminum sheets at precise angles. Assemblers learned to install electrical systems, hydraulics, and gun turrets. Mechanics were trained to maintain engines under factory conditions. Teams became highly specialized, with each worker mastering a single component or assembly step. This division of labor allowed factories to produce aircraft at unprecedented speed, but it also demanded discipline, oversight, and careful scheduling to avoid bottlenecks. Innovation in workflow transformed production. Borrowing principles from automobile assembly, factories adapted moving assembly lines for large and fragile aircraft structures. Jigs and cranes allowed workers to assemble wings, fuselages, and tails in sections, reducing physical strain and increasing efficiency. Subassemblies were tested individually before integration, minimizing costly errors. These techniques were refined over months, creating a production rhythm that could sustain tens of thousands of aircraft without sacrificing safety or performance. Industrial engineers became as critical as pilots in ensuring that the planes would dominate the skies. Government oversight accelerated the pace of production while maintaining accountability. Inspectors monitored quality at every stage, ensuring that each aircraft met military specifications. Deviations could result in catastrophic failure in combat, so rigorous checks became routine. Factories implemented multiple layers of inspection, from component-level evaluation to full-flight tests. Pilots and engineers collaborated to identify recurring problems and refine manufacturing processes. The result was a dynamic feedback loop in which combat experience informed production, which in turn produced aircraft capable of surviving the demands of modern warfare. Competition among manufacturers also drove innovation. Boeing, Lockheed, Douglas, North American Aviation, and other firms competed for contracts, striving to meet ambitious quotas without compromising quality. Rivalries spurred technical ingenuity, faster workflows, and inventive solutions to recurring production challenges. Each company specialized in certain models, creating centers of expertise that accelerated innovation. The interplay of competition and collaboration ensured that American aircraft would not only be produced in vast quantities, but would also incorporate the latest advancements in speed, durability, armament, and avionics. By the end of 1942, these combined efforts transformed America's aircraft industry into an industrial marvel. Designs once considered difficult or impractical to mass produce were now rolling off assembly lines in unprecedented numbers. From the factories of Seattle to the plants of Southern California, the nation had built an aerial arsenal capable of challenging and eventually dominating Axis air power. The stage was set for the American planes that would redefine aerial combat, from the skies over Europe to the Pacific Islands, shaping the course of the war and cementing the United States as a global industrial and military power. The engine of aircraft production was not fueled by machines alone. Millions of workers, many of them women, became the heartbeat of the factories that would dominate the skies. With millions of men drafted into military service, the labor vacuum threatened to stall production. In response, the U.S. government and industry launched campaigns to recruit women into roles that had once been closed to them. Rosie the Riveter was not merely a cultural icon. It was a reality. Women learned to rivet aluminum fuselages, install hydraulic systems, and operate presses and lathes with a precision previously demanded only of men. Their entry into the workforce transformed social norms and demonstrated that the nation's survival depended on the full mobilization of its population. Training programs were intensive and unforgiving. New workers were taught to master complex tools, read technical schematics, and understand the tolerances that separated a functional aircraft from a catastrophic failure. Supervisors implemented rigorous drills to ensure consistency, with repeated inspections to prevent mistakes. Mistakes could be deadly. A misaligned wing or improperly installed engine could spell disaster for a pilot in combat. Yet, despite the pressure and intensity, the workforce adapted quickly, demonstrating ingenuity and resilience. The pace of learning and efficiency became legendary, proving that human adaptability was as vital as any assembly line innovation. The factories themselves became microcosms of wartime America, a crucible where social change and industrial innovation collided. Women, African Americans, and immigrants all filled roles that had been inaccessible in peacetime. In some cities, women outnumbered men on the factory floor, managing heavy machinery and performing complex tasks that required both strength and dexterity. The daily reality of war production demanded collaboration, and hierarchies based solely on gender or race were challenged by necessity. Though prejudice persisted, the results were undeniable. Aircraft were being built faster and more efficiently than anyone had imagined possible. Racial integration within the workforce was partial but impactful. In many northern factories, African Americans were employed in assembly lines, foundries, and maintenance shops, often in roles critical to production. They faced discrimination, unequal pay, and limited promotion opportunities, yet their labor was essential to meeting quotas. Their contributions, though often overlooked in official reports, demonstrated both skill and resilience. Black workers, like their female counterparts, became symbols of the broader capacity of American society when pressed to its limits. Every completed airframe, every installed engine, was a testament to their ingenuity and dedication. Union involvement was another crucial factor. While some labor disputes arose over pay, hours, and working conditions, unions helped maintain stability, negotiate fair treatment, and prevent production slowdowns. Strikes were rare, as workers were motivated by both patriotism and a sense of historical purpose. Labor leaders recognized that the war was as much an industrial battle as a military one, and they leveraged their influence to ensure that factories ran smoothly, materials flowed efficiently, and production schedules were maintained. The collaboration between labor, government, and management became a defining feature of the wartime industrial effort. The psychological toll of such labor was immense. Workers labored 12-hour shifts, often 6 days a week, in hot, noisy, and dangerous environments. Accidents were common, and fatigue tested both concentration and morale. Yet the workers persevered, driven by the knowledge that each plane they assembled would carry soldiers, bombers, and supplies into combat zones. The stakes were personal as much as national. The factory floor became a silent battlefield, where the victories were measured not in territory gained, but in airframes completed, engines tested, and bombs delivered accurately on target. Innovation and workflow continued to accelerate. Women and men on the assembly lines contributed ideas for efficiency, creating shortcuts that saved time without compromising safety. Modular construction techniques, standardized parts, and moving assembly lines were refined continuously. Factories became laboratories for industrial ingenuity, testing methods that would influence manufacturing long after the war ended. Each improvement in speed or quality multiplied across thousands of planes, dramatically increasing the United States' capacity to project air power globally. By the close of 1943, the scale of production achieved by this workforce was staggering. Factories produced thousands of aircraft each month, with workers completing planes at a pace previously thought impossible. The human story behind this achievement: millions of men and women adapting, learning, and innovating under extreme pressure, became inseparable from the narrative of American aerial supremacy. The planes that dominated the skies were not merely machines. They were embodiments of industrial collaboration, human endurance, and a society mobilized for total war. Transforming advanced aircraft designs from prototypes into mass-produced warplanes was a feat that tested the limits of engineering, logistics, and management. The P-51 Mustang, B-17 Flying Fortress, and the B-29 Superfortress were not just airplanes. They were complex systems demanding precision, coordination, and ingenuity at every stage of production. Prototypes underwent rigorous testing in wind tunnels and flight trials, revealing flaws that could cost lives if left uncorrected. Engineers then had to reconcile the need for combat performance with the realities of large-scale manufacturing, simplifying structures, standardizing parts, and ensuring that components could be replicated accurately in multiple factories across the country. One of the most significant challenges lay in materials engineering. Aluminum, essential for lightweight yet durable airframes, had to be alloyed, shaped, and treated in ways that could withstand the stresses of combat. Steel, used for landing gear, gun mounts, and engine components, required precision heat treatment to avoid catastrophic failure. Rubber, glass, and wiring had to meet rigorous specifications, all while being produced in massive quantities under wartime scarcity. Engineers and production managers worked closely to develop substitutes, adjust tolerances, and create contingency plans to keep planes rolling off assembly lines despite material shortages. Assembly lines were redesigned to accommodate the size and complexity of these aircraft. Moving assembly platforms, cranes, and modular subassemblies allowed workers to construct wings, fuselages, and tails simultaneously before final integration. Every step was timed, every motion optimized, and every station staffed with specialists who focused on a single task with surgical precision. This division of labor, combined with modular production techniques, drastically reduced construction time, from months to weeks in some cases, while maintaining the structural integrity required for combat missions over Europe and the Pacific. Engine production represented another engineering marvel. Radial engines, such as the Pratt & Whitney R-2800, were intricate machines containing thousands of precision parts. Factories developed specialized machining centers, jigs, and testing rigs to ensure that every engine met stringent performance standards. Test benches simulated the stresses of combat flight, evaluating engines for vibration, heat tolerance, and reliability. Any failure could mean disaster for the pilot, so quality control was relentless. The successful production of these engines in massive quantities became a cornerstone of American air dominance. Innovation extended to electronics, avionics, and weaponry integration. Bombers required complex navigation, communication, and targeting systems, while fighters demanded responsive controls and armament capable of precision engagement. Wiring looms were pre-assembled in factories, radio and radar components were tested rigorously, and gun turrets were calibrated for accuracy. The integration of these systems required a level of industrial and engineering coordination that rivaled military planning itself. Engineers and factory managers developed feedback loops, where issues discovered in flight tests prompted rapid modifications in production lines. Coordination between subcontractors and primary manufacturers became critical. Engines, propellers, radios, landing gear, and other components were often produced in separate facilities, then shipped to final assembly plants. Any delay at a subcontractor could halt the production of dozens of aircraft, so logistics, scheduling, and quality assurance were essential. Transportation networks, from railroads to truck convoys, were integrated into production planning, ensuring that each factory received the precise materials needed at the right time. The scale of this coordination was unprecedented in American industry. Labor efficiency and morale were constant concerns. Supervisors encouraged workers to suggest improvements, streamline workflows, and identify potential bottlenecks. Safety protocols were enforced rigorously, yet accidents were unavoidable given the scale and intensity of production. Workers endured heat, noise, and fatigue, yet the sense of purpose, knowing that each aircraft might determine the fate of soldiers, sailors, and pilots in combat, fueled dedication. Human ingenuity, endurance, and adaptability became just as important as any tool or machine in ensuring the success of mass production. By late 1943, the system had matured into an industrial juggernaut. Aircraft rolled off assembly lines in record numbers. Engines roared to life in test stands, and entire fleets were delivered to the Army, Air Forces, and Navy with unprecedented speed. The American capacity to mass-produce cutting-edge planes created a decisive advantage in the air, allowing the Allies to overwhelm Axis forces not only with strategy and skill, but with sheer quantity and reliability. The skies were no longer dominated by a few elite squadrons. They belonged to a nation that had harnessed industrial power on a scale never before seen, proving that American ingenuity could translate design brilliance into overwhelming operational capacity. With mass production achieving unprecedented output, the United States began supplying the skies with a steady stream of long-range bombers capable of striking deep into enemy territory. The B-17 Flying Fortress became the symbol of American aerial power, engineered to endure flak, fighter attacks, and long missions over Europe. Every plane that left the factory carried not only bombs but the labor, ingenuity, and sacrifice of thousands of workers and engineers. Its design balanced speed, defensive armament, and payload capacity, making it a formidable weapon that could penetrate heavily defended airspace while protecting its crew as best as possible. The B-24 Liberator complemented the B-17, offering extended range and greater payload flexibility. Factories in California and New York were retooled to crank out Liberators at a staggering pace, with each aircraft undergoing hundreds of inspections before it was deemed combat-ready. Assembly lines moved with machine-like precision, and engineers continued to refine components to increase reliability and reduce weight. Bombers required more than raw metal and engines. They needed communication systems, targeting instruments, and defensive weaponry, all integrated seamlessly to ensure survival over enemy territory. Bombardiers and crews relied on precision, and the manufacturing process had to guarantee uniformity across every plane. Norden bomb sights, advanced radios, and defensive turrets were installed with painstaking care. Mistakes could cost lives in the form of missed targets, malfunctioning weaponry, or structural failure under combat stress. Quality assurance teams, engineers, and test pilots collaborated continuously to ensure that mass production did not compromise effectiveness. Every B-17 or B-24 leaving the factory was the product of both industrial might and human vigilance, a machine built to survive and deliver devastation. The Pacific Theater demanded a different set of innovations. The B-29 Superfortress, designed for long-range missions over Japan, pushed industrial engineering to the limit. It incorporated pressurized cabins, remote-controlled gun turrets, and advanced engines capable of sustained high-altitude flight. Factories in Wichita, Kansas, and Renton, Washington, adapted to produce these sophisticated aircraft in volume, overcoming challenges in engine reliability, weight distribution, and assembly complexity. Workers faced the daunting task of translating revolutionary designs into operational warplanes under tight deadlines, often learning new skills on the job to meet production goals. Mass production allowed the U.S. to maintain a relentless bombing campaign, shifting the balance in both theaters of war. Crews knew that spare planes were always on the way, bolstering morale even when losses were high. The sheer volume of bombers created strategic options unavailable to Axis forces, enabling sustained raids on industrial centers, transportation networks, and military installations. Factories thus became an extension of the battlefield, their output determining not only the number of sorties but the intensity and reach of the air campaign. Maintenance and repair were integral to sustaining this aerial dominance. Field depots and forward bases relied on standardized parts produced en masse to keep planes operational. Engines could be swapped, wings repaired, and electronics recalibrated using components manufactured thousands of miles away. This system of supply and repair multiplied the effectiveness of every aircraft produced, turning industrial output into enduring combat power. The lines between factory floor and frontline airfield blurred as planes were continually cycled, upgraded, and returned to battle. The human cost of bomber production and deployment was never abstract. Thousands of workers labored in dangerous, exhausting conditions to meet quotas, while crews flying these bombers faced lethal enemy fire. Factories and airfields became interlinked nodes of sacrifice and effort, each feeding into a larger system aimed at overwhelming enemy capabilities. Every mission over Germany or Japan reflected the intertwined contributions of engineers, laborers, mechanics, and pilots, a symphony of effort culminating in strategic impact. By mid-1944, the United States had achieved an industrial and operational tempo unmatched in history. Factories produced thousands of bombers, engines, and critical components each month, sustaining an air offensive that stretched Axis defenses to breaking point. The combination of human ingenuity, disciplined labor, and engineering excellence had transformed the U.S. into the preeminent aerial power. The planes that dominated the skies were not simply weapons. They were the embodiment of an entire nation mobilized, a testament to the scale and capability of American industry in total war. While bombers symbolized the strategic reach of American air power, fighter aircraft became the indispensable instruments of tactical supremacy. Planes like the P-51 Mustang, P-47 Thunderbolt, and F-4U Corsair combined speed, maneuverability, and firepower to dominate skies over Europe, North Africa, and the Pacific. Mass-producing these high-performance fighters presented unique challenges. Unlike bombers, which prioritized payload and endurance, fighters required precision engineering for aerodynamics, engine output, and weight distribution. Every modification impacted flight characteristics, forcing engineers and assembly teams to innovate rapidly while maintaining consistency across thousands of airframes. The P-51 Mustang exemplified the integration of design ingenuity and production efficiency. Its initial prototype impressed engineers with its sleek airframe and laminar flow wing, but adapting it to mass production demanded new jigs, standardized parts, and streamlined assembly procedures. Factories in Inglewood, California, and Dallas, Texas, implemented specialized stations where wings, fuselages, and tail sections were built simultaneously and then integrated in final assembly lines. This modular approach allowed for unprecedented production speed without compromising structural integrity or performance. Engines for fighters posed another critical bottleneck. The Rolls-Royce Merlin engine, used in the P-51 and the Pratt & Whitney R-2800, powering the P-47 and F-4U, were marvels of mechanical engineering but difficult to produce at scale. Factories devised synchronized machining, specialized tooling, and rigorous quality checks to ensure each engine met demanding tolerances. Engine failures in combat were catastrophic, so test stands, simulation rigs, and pilot feedback loops became essential. The coordination between engine manufacturers, assembly plants, and field maintenance teams created a seamless network that translated industrial production into battlefield effectiveness. Armament integration added layers of complexity. Fighters carried machine guns, cannons, bombs, and rockets, all requiring precise installation, calibration, and alignment. Factories trained specialists to handle weapons installation, ensuring that firing mechanisms operated reliably under the stress of combat. Even minor deviations could compromise accuracy or safety, so inspectors meticulously evaluated every system before the aircraft left the line. The result was a fleet of fighters that could engage enemy aircraft, escort bombers, and execute ground attack missions with lethal precision. Workforce adaptability was crucial to this success. Women and men, many new to aviation work, mastered intricate tasks such as riveting thin aluminum skins, installing hydraulic systems, and wiring electronic controls. African American workers, often facing discrimination, contributed significantly to assembly lines and component production, proving their skills under pressure. Factory managers fostered efficiency by encouraging problem-solving and cross-training, ensuring that production bottlenecks were swiftly addressed. Human ingenuity amplified technological capability, transforming labor into an essential force multiplier. Supply chain logistics dictated the pace of production. Fighter aircraft relied on a steady flow of engines, propellers, avionics, and armament, much of it produced in separate facilities across the country. Railroads, trucks, and ports were integrated into a system that delivered parts precisely when needed. Any delay could halt the assembly of hundreds of planes, underscoring the delicate balance between industrial capacity and logistical coordination. By maintaining this network, the United States ensured that factory output translated into operational squadrons ready for combat deployment. Test flights and quality assurance were ongoing processes. Each fighter was flown by trained pilots to detect issues invisible on the assembly line: engine quirks, control sensitivities, or weapon malfunctions. Feedback from these flights informed engineers and production supervisors, prompting incremental improvements that enhanced performance and reliability. This iterative process ensured that mass-produced fighters were not merely functional, but formidable adversaries capable of matching or exceeding enemy aircraft in combat. By early 1944, U.S. fighter production had reached unprecedented scale. Factories produced hundreds of aircraft monthly, supporting global operations and overwhelming Axis air forces with both quantity and quality. The combination of advanced engineering, innovative mass production techniques, skilled labor, and logistical coordination created a fighter fleet that dominated the skies. American industry had transformed raw materials, human effort, and ingenuity into machines that could secure air superiority, protect bombers, and change the course of aerial warfare. Mass-producing planes was only part of the challenge. Getting them from factory floors to active combat zones required a logistical effort of unparalleled scale. Aircraft had to be disassembled for transport, crated, and shipped across oceans to reach forward bases in England, North Africa, and the Pacific. Every wing, fuselage, and engine component traveled on railcars, trucks, and cargo ships, coordinated by an intricate network of military and civilian personnel. Delays or losses at any stage could cripple a squadron, so meticulous planning and redundancy were essential. The aircraft themselves were fragile instruments of war, and the journey from production to deployment demanded as much precision and care as assembly. In Europe, ferrying newly built fighters and bombers required pilots to navigate treacherous weather, enemy airspace, and unfamiliar terrain. Long-distance flights across the North Atlantic involved refueling stops in Canada, Greenland, and Iceland, each stage coordinated to minimize risk. Pilots relied on navigation charts, radio beacons, and rudimentary weather forecasting, while ground crews prepared runways for arrivals under pressure. The success of this global distribution network ensured that production numbers translated directly into combat power, keeping Allied air forces supplied and ready for sustained operations. In the Pacific theater, the logistical challenges were even greater. Island-hopping campaigns demanded the rapid deployment of aircraft across vast stretches of ocean. Fighters and bombers were often shipped in parts to forward bases, then reassembled by mechanics and engineers under primitive conditions. Fuel, ordnance, and spare parts had to arrive on the same ships or via airlift, creating a fragile supply chain. Every delay or miscalculation risked grounding entire squadrons, making the orchestration of industrial output and frontline operations a complex ballet of timing and coordination. Maintenance and repair became a critical extension of production. Factories produced standardized parts not only for new planes, but also for replacing worn or damaged components at forward bases. Engines could be swapped, wings repaired, and avionics recalibrated using these mass-produced spares. This system ensured that aircraft longevity and operational readiness remained high, turning the industrial might of the United States into a sustainable force that could endure months of combat attrition. The feedback loop between combat experience and production adjustments further refined both planes and parts. The human element in logistics was indispensable. Ground crews, mechanics, and pilots worked around the clock to assemble, repair, and deploy aircraft. Their labor was relentless and dangerous, often conducted under threat of enemy attack. Yet their commitment ensured that the planes leaving American factories could reach combat zones in peak condition. Training programs emphasized efficiency and precision, teaching crews to assemble engines, rig control systems, and arm weaponry with minimal error. Each aircraft delivered to the front lines represented the combined efforts of thousands of individuals working in harmony across thousands of miles. Strategic planning played a pivotal role. The U.S. military coordinated with manufacturers to prioritize aircraft types based on theater needs. Long-range bombers were shipped to England for strategic raids over Germany, while fighters were directed to North Africa or the Pacific for tactical missions. This coordination ensured that production output met the shifting demands of the war, optimizing resources and maximizing combat effectiveness. Factories adapted quickly to changing requirements, demonstrating a remarkable level of flexibility for an industrial operation of such scale. Innovation in transportation accelerated deployment. Crates were designed for easy handling and rapid assembly, and new methods for airlifting parts reduced reliance on long-sea voyages. Engineers and logisticians collaborated to streamline packaging, improve durability during transit, and facilitate rapid assembly at forward bases. These innovations allowed squadrons to be operational faster, directly translating industrial production into battlefield dominance. The speed of delivery became a strategic advantage, enabling the Allies to respond dynamically to enemy movements and campaigns. By 1944, the integration of production and logistics had reached a level never before achieved in human history. Aircraft rolled off assembly lines, traversed oceans, and were assembled and deployed in weeks rather than months. The combination of mass production, logistical precision, and human ingenuity ensured that the United States could sustain global air operations simultaneously in Europe and the Pacific. The skies above enemy territory were filled with planes born of industrial might, the product of innovation, coordination, and the tireless efforts of countless workers, mechanics, and pilots who transformed steel and aluminum into tools of victory. As production reached unprecedented scales, American engineers faced another challenge: keeping aircraft technologically ahead of enemy designs. Mass production could not come at the expense of innovation. Designers and engineers continuously refined airframes, engines, armament, and avionics to meet evolving battlefield demands. The P-51 Mustang, for example, underwent modifications to improve high-altitude performance, while the B-29 Superfortress integrated remote-controlled gun turrets and pressurized cabins, features unheard of in previous generations of aircraft. Factories adapted swiftly, implementing design changes without halting production, a feat that required remarkable coordination between engineers, managers, and assembly workers. Aerodynamic innovation became crucial. Engineers studied airflow, wing shapes, and fuselage contours to maximize speed, stability, and maneuverability. Laminar flow wings reduced drag, allowing fighters like the Mustang to escort bombers deeper into enemy territory. Bombers were reinforced to withstand flak, turbulence, and long-range missions over hostile territory. Engineers and technicians collaborated closely with test pilots, translating flight data into production adjustments, ensuring that mass-produced aircraft maintained combat effectiveness while incorporating cutting-edge advancements. Engines were continually upgraded to meet increasing performance requirements. The Rolls-Royce Merlin engine, adapted for U.S. production, and the Pratt & Whitney R2800 became symbols of reliability and power, yet they were constantly improved for higher output and durability. Factories developed new machining processes, precision tools, and assembly techniques to accommodate these upgrades without slowing production. Every engine that left the line represented a careful balance between mass production efficiency and engineering excellence, ensuring that American aircraft could outperform enemy counterparts in both speed and endurance. Weapons integration also evolved rapidly. Fighters carried synchronized machine guns, cannons, and rockets, while bombers incorporated advanced bomb sights, turrets, and defensive armament. Factories designed specialized stations to assemble and test these systems, and inspectors rigorously verified that all components functioned correctly. Even minor errors in installation could compromise mission effectiveness, so strict protocols ensured that weapons systems were as reliable as the aircraft themselves. The complexity of these systems underscored the incredible precision required in American aircraft production. Avionics and communications became increasingly sophisticated. Bombers relied on radar navigation and targeting, while fighters used radios for coordinated maneuvers and engagement with ground controllers. Factories produced and installed these electronics at scale, a process that required specialized knowledge and careful quality control. Teams of technicians tested every circuit and system, simulating combat conditions to guarantee performance under duress. The integration of electronics into aircraft production represented a leap forward in both technology and industrial capability. The pressure of wartime necessity drove rapid problem-solving and innovation. Factories encountered production bottlenecks, material shortages, and design flaws, yet engineers and managers devised creative solutions, from modular assembly to substitute materials. Continuous feedback from frontline operations informed adjustments in design and manufacturing, creating a dynamic loop where industrial output was constantly refined. This ability to adapt and innovate under pressure became a hallmark of American aircraft production, ensuring that mass-produced planes remained at the forefront of aerial combat. Workforce ingenuity contributed directly to these innovations. Factory workers suggested improvements in assembly techniques, tools, and part layouts, often resulting in faster production without sacrificing quality. Their practical experience complemented the theoretical knowledge of engineers, bridging the gap between design and production. This collaborative culture accelerated the implementation of technological upgrades and allowed factories to maintain high output while improving performance, a feat few nations could replicate under wartime conditions. By 1944, American aircraft production had achieved a synergy of speed, scale, and technological superiority. Factories were not merely churning out machines. They were continuously producing innovations that translated directly into combat advantage. Fighters and bombers became faster, stronger, and more reliable with each production cycle. This relentless drive for improvement, combined with industrial might and human ingenuity, ensured that U.S. aircraft could dominate the skies, turning mass production into a strategic weapon and securing aerial supremacy for the Allied forces. The enormous industrial output of American aircraft was only half the battle. The planes required skilled pilots capable of exploiting their speed, maneuverability, and firepower. Flight training programs expanded dramatically to meet the influx of new planes, creating a network of civilian and military schools that churned out thousands of aviators. Cadets learned navigation, gunnery, formation flying, and instrument reading in increasingly realistic simulations and practice flights. Each training program was closely tied to the aircraft being produced, ensuring that pilots were familiar with the precise controls, quirks, and limitations of their assigned planes. Fighter pilots trained to operate P-51 Mustangs, P-47 Thunderbolts, and F-4U Corsairs, mastering high-speed maneuvers and aerial combat tactics. They practiced dogfighting, escort missions, and ground attack strategies, learning to respond instinctively to enemy threats. Bomber crews were trained in formation flying, long-range navigation, and precision bombing techniques, with specialized roles for pilots, co-pilots, navigators, bombardiers, and gunners. Each crew member had to understand not only their responsibilities, but also how their actions affected the performance and survivability of the entire aircraft. Training programs had to adapt quickly to technological advances in aircraft design. As new models rolled off assembly lines, instructors updated curricula to reflect improved engines, avionics, and weapon systems. Pilots and crew trained on simulators, mock-up cockpits, and modified trainer aircraft before flying the latest production models. This ensured that mass-produced planes were not only delivered to the front lines, but were also operated to their maximum effectiveness, translating industrial capacity into battlefield performance. Logistics of training mirrored production scale. Airfields, barracks, and maintenance facilities expanded to accommodate thousands of cadets and instructors. Spare parts, fuel, and practice munitions were delivered in precise quantities to support uninterrupted training. Maintenance crews learned to repair the very planes students would eventually fly in combat, creating a pipeline of readiness that connected factories, training bases, and operational squadrons. The flow of planes and pilots became a coordinated system, ensuring that new aircraft could enter active service without delay. The human dimension of training was intense. Cadets faced rigorous physical and mental challenges, enduring long flights, extreme weather, and simulated combat scenarios designed to push them to their limits. Mistakes could be fatal, and instructors emphasized discipline, situational awareness, and quick decision-making. The pressure mirrored the realities of combat, preparing pilots not only to operate advanced aircraft, but also to survive the chaos and danger of modern aerial warfare. Integration of female pilots into non-combat roles further amplified production effectiveness. The Women Air Force Service Pilots, WASP, ferried newly built aircraft from factories to training bases and operational units, allowing male combat pilots to focus on combat preparation. These women faced dangerous conditions, flying untested planes, often in challenging weather, demonstrating both skill and courage. Their contribution was crucial in connecting industrial output with operational readiness, ensuring that mass-produced aircraft reached the pilots who would take them into battle. Feedback loops from combat operations influenced training programs. Lessons learned from missions over Europe, North Africa, and the Pacific informed adjustments in tactics, flight techniques, and aircraft handling. Pilots returned from combat to share insights on enemy strategies, mechanical quirks, and effective maneuvers. These insights were incorporated into training, ensuring that new aviators benefited from the hard-earned experience of those already engaged in battle. This continuous learning process amplified the effectiveness of mass-produced aircraft by pairing them with highly skilled operators. By 1944, the combination of industrial output and comprehensive pilot training created an air force capable of sustained operations across multiple theaters. Aircraft flowed from factories to training bases to combat units in a seamless chain, and pilots were prepared to exploit every advantage the planes offered. The United States had transformed not only its industrial capabilities, but also its human capital, ensuring that the planes dominating the skies were paired with crews trained, disciplined, and ready to turn American manufacturing might into decisive air power. While American factories ramped up production, they faced extraordinary pressures both from within and outside the war effort. Labor shortages, material rationing, and technical challenges constantly threatened to slow output. Yet, the wartime spirit on the home front ensured that these obstacles were met with ingenuity and determination. Women and minorities filled positions traditionally reserved for men, learning new skills and adapting quickly to meet the demands of aircraft assembly. Entire communities rallied behind the effort, from civic groups organizing transportation to the factories to local businesses supplying food, uniforms, and shelter for the growing workforce. Factories became intense environments, with noise, heat, and repetitive tasks pushing workers to their physical and mental limits. Accidents were common, from burns to falls, yet morale remained high because employees understood that every rivet, panel, and engine part contributed directly to the fight abroad. Safety protocols evolved rapidly, and supervisors emphasized both efficiency and protection. Despite the challenges, production continued to accelerate, demonstrating the resilience and adaptability of the American workforce under extreme conditions. Material shortages forced engineers and manufacturers to innovate. Aluminum, rubber, and steel were tightly controlled, prompting the development of substitutes, efficient cutting patterns, and waste reduction techniques. Factories optimized the use of raw materials to ensure maximum output, often reconfiguring assembly lines on the fly to accommodate shifting availability. The ability to adapt production processes under constraints became as important as speed, creating a flexible industrial system that could endure both wartime demands and logistical hurdles. The threat of sabotage and espionage added another layer of tension. Factories were guarded, and security measures intensified as the importance of aircraft production became clear. Workers were educated about the critical nature of their tasks, while intelligence agencies monitored potential threats to ensure continuity of output. Even small disruptions could ripple through the complex network of production and supply, highlighting how interconnected and vulnerable the industrial war effort truly was. Coordination with suppliers was essential to maintaining production flow. Thousands of subcontractors across the nation manufactured engines, propellers, electronics, and armament components. Delays at a single supplier could halt hundreds of aircraft in assembly. To prevent such bottlenecks, the War Production Board meticulously scheduled deliveries, monitored inventories, and implemented contingency plans. Railroads, ports, and trucking networks became extensions of the factories, ensuring that raw materials and finished components moved efficiently from one point to another. Worker morale was also bolstered by national propaganda and a pervasive sense of purpose. Posters, films, and radio programs reminded the workforce that their labor was critical to defeating Axis powers. Celebrations of production milestones, bonuses, and awards further encouraged dedication. The emotional and psychological investment of the homefront workforce became as significant as their physical labor, instilling pride and resilience that kept factories running at peak capacity. Technological advancements were continuously integrated into production despite these pressures. Assembly lines evolved to accommodate new aircraft models and upgrades, from reinforced bombers to faster, better-armed fighters. Engineers worked alongside line managers to implement improvements without interrupting output, ensuring that innovation and mass production progressed hand in hand. This ability to incorporate cutting-edge technology into large-scale manufacturing distinguished American aircraft production from that of other nations. By late 1943, the synergy of human effort, technological innovation, and logistical coordination had created an industrial juggernaut. Factories across the United States produced aircraft, engines, and critical components at a pace and scale unmatched anywhere in the world. The resilience of workers, the ingenuity of engineers, and the dedication of communities ensured that mass-produced aircraft would dominate the skies, transforming American industry into a decisive weapon of war. The homefront effort had become inseparable from the combat it supported, proving that victory in the air began hundreds of miles from the battlefield, in the sweat, skill, and sacrifice of factory floors. The B-29 Superfortress represented the pinnacle of American aircraft engineering and industrial achievement. Conceived for long-range bombing over Japan, it pushed the limits of technology with pressurized cabins, remote-controlled gun turrets, and advanced avionics. Yet producing such a sophisticated machine in mass quantities was a staggering challenge. Factories in Wichita, Kansas, and Renton, Washington, were transformed into sprawling production complexes, where thousands of workers coordinated to assemble every component with extraordinary precision. Every rivet, cable, and engine had to meet tolerances that left no margin for error, for the plane would carry crews thousands of miles over enemy territory. Engine production for the B-29 was particularly difficult. Its Wright R-3350 duplex Cyclone engines were powerful but prone to overheating, demanding rigorous testing, precise assembly, and constant quality control. Factories developed specialized tooling, inspection rigs, and cooling solutions to prevent failures. Mechanics and engineers worked tirelessly to refine engine reliability, knowing that each superfortress depended on flawless performance for both the safety of its crew and the success of its mission. The scale and complexity of these engines exemplified the challenges of translating cutting-edge design into mass-produced reliability. The B-29's fuselage, wings, and tail structures were modularized to allow simultaneous assembly of subcomponents. Jigs and cranes moved massive sections through assembly lines, where workers installed electrical systems, hydraulic lines, and armament stations. Each station required specialized skill, and teams of inspectors verified each installation. Despite the immense size and complexity of the superfortress, factories achieved production times previously considered impossible, proving that mass production and advanced engineering could coexist at the highest level. Avionics and weapons systems integration added layers of intricacy. Remote-controlled gun turrets, radar navigation, and bombing computers had to function flawlessly in unison. Electronics technicians meticulously calibrated each system, while test flights simulated combat scenarios to verify accuracy. Lessons learned from early deployments were fed back into production lines, resulting in continuous improvements that increased both effectiveness and survivability. The B-29 became a living testament to the synergy between industrial capacity and technological innovation. Labor challenges were immense. Thousands of workers, many unfamiliar with such complex aircraft, were trained rapidly to perform specialized tasks. Women and minorities contributed in critical roles, learning to handle machinery, electrical systems, and intricate assemblies. Safety remained a constant concern, with hundreds of potential failure points in each plane. Yet dedication and teamwork ensured that output continued without compromising quality, illustrating how human skill could match industrial ambition to produce unprecedented aerial machines. Logistics for the B-29 were formidable. Parts were sourced from hundreds of suppliers across the United States and had to be delivered on schedule to avoid halting production. Engines, wings, fuselage sections, and avionics traveled via rail, truck, and air transport to final assembly plants. Any delay could cascade into the production schedule, threatening the delivery of aircraft to the Pacific Theater. The careful orchestration of supply chains turned the United States into a factory-spanning, continent-wide enterprise capable of supporting global air operations. Once assembled, each B-29 underwent rigorous flight testing. Pilots checked controls, engines, avionics, and defensive systems under conditions simulating the most extreme missions. Adjustments and refinements were fed back into production, ensuring that each plane leaving the factory incorporated the latest solutions to combat challenges. This iterative process allowed mass production to enhance, rather than diminish, technological sophistication, producing aircraft that were both abundant and highly capable. By 1944, the B-29 program had matured into an industrial marvel, producing planes in numbers sufficient to sustain a strategic bombing campaign over Japan. The superfortress symbolized the fusion of American engineering, labor, and logistical expertise, demonstrating that mass production could deliver not just quantity, but unmatched quality and innovation. These aircraft would become instruments of decisive power in the final stages of the Pacific War, proving that American industry could transform ingenuity into overwhelming aerial dominance. By 1944, the interdependence of bombers and fighters became the cornerstone of Allied air strategy. While long-range bombers like the B-17, B-24, and B-29 delivered destruction to enemy infrastructure, they relied on fighter aircraft for protection. The P-51 Mustang, with its extended range and maneuverability, provided escort deep into enemy territory, ensuring that strategic bombing campaigns could proceed with reduced losses. The industrial system that produced these aircraft at scale was intricately linked. A surge in bomber production required corresponding increases in fighter output, engines, and trained pilots, demanding coordination across factories, training bases, and supply networks. Mass production techniques were adapted to synchronize bomber and fighter outputs. Assembly lines, tooling, and labor schedules were designed to maintain consistent delivery rates for both categories of aircraft. Engine manufacturers allocated production to meet the requirements of multiple models, while logistics teams ensured timely delivery to training bases and operational units. This synchronization ensured that combat operations could deploy balanced formations of bombers and fighters, maximizing their effectiveness while minimizing vulnerability to enemy interception. The deployment of escort fighters transformed strategic bombing. Before the P-51 and similar aircraft could accompany bombers for hundreds of miles, Allied raids suffered high attrition rates from Luftwaffe interceptors. The introduction of mass-produced, long-range fighters shifted the calculus, allowing bombers to strike deeper targets with fewer losses. This success was not only a testament to the planes themselves, but to the industrial infrastructure that produced them and the training programs that prepared pilots to operate in coordinated formations under combat conditions. Industrial flexibility allowed factories to respond to operational feedback. Combat reports revealed performance gaps or mechanical issues, which engineers addressed without halting production. Modifications to armament, fuel systems, or structural components were implemented on assembly lines, creating a continuous improvement cycle. This integration of operational experience into production ensured that mass-produced aircraft remained tactically superior, reinforcing the link between industrial output and battlefield success. Coordination extended beyond aircraft to supporting systems. Spare parts, ordnance, and maintenance crews were deployed alongside planes to ensure that squadrons remained operational. Forward airfields required engines, replacement wings, and avionics modules, all standardized for rapid repair and replacement. Factories produced these items in parallel with the aircraft themselves, creating a resilient network capable of sustaining extended campaigns. The system of supply and repair multiplied the effectiveness of each plane, ensuring that industrial output translated into persistent airpower. Pilot training emphasized the integration of fighters and bombers. Escort tactics, formation flying, and communications protocols were refined to ensure that aircrews could respond seamlessly to threats. Practice missions simulated enemy interception, bombing runs, and coordination under fire. This preparation allowed mass-produced aircraft to perform optimally in real combat, with each pilot and crew understanding their role in the larger strategy of air supremacy. The human and industrial elements combined to create a synergistic force. Factories produced aircraft in record numbers, while pilots and crews were trained to operate them with precision. Maintenance teams ensured operational readiness, and supply chains delivered the necessary parts and fuel. Every successful bombing mission reflected the orchestration of thousands of people, from riveters in California to fighter pilots in England, each contributing to a complex, continent-spanning enterprise that turned American industrial power into decisive air dominance. By the end of 1944, the integration of bombers and fighters, underpinned by mass production and logistical excellence, had decisively shifted the balance of air power in favor of the Allies. American aircraft dominated skies over Europe and the Pacific, illustrating the transformative impact of industry, innovation, and human coordination. The success of this system demonstrated that mass-produced planes, combined with skilled crews and strategic foresight, could achieve what no single technological breakthrough alone could: sustained and overwhelming aerial superiority. While the factories, assembly lines, and logistics networks symbolized American industrial might, the human cost of producing and operating these aircraft was immense. Workers endured long hours in harsh, noisy, and sometimes dangerous conditions to keep up with production quotas. Heat, chemical exposure, and the constant hum of machinery tested both body and mind. Accidents, though minimized through rigorous safety protocols, were inevitable, and many workers bore injuries as a testament to their contribution. Each aircraft that left the factory carried with it the labor, sacrifice, and resilience of thousands of individuals who had made the impossible possible. Pilots and aircrews faced even more direct risks. Every combat mission brought the possibility of flak, enemy fighters, mechanical failure, or navigational error. The planes themselves were marvels of engineering, yet they could not compensate for human vulnerability. Training mitigated some of these risks, but countless lives were lost in the skies over Europe, North Africa, and the Pacific. Each sortie underscored the fragile balance between technological innovation and human endurance. The air war was as much a testament to courage as it was to industrial achievement. The stress extended to maintenance crews and ground personnel. Mechanics worked around the clock, often in primitive conditions at forward airfields, repairing engines, replacing damaged components, and keeping planes flight-ready. Every missed part or delayed repair could compromise a mission or endanger a crew. These behind-the-scenes efforts were crucial to sustaining the relentless tempo of aerial operations, yet they remained largely invisible in the narrative of war. Their work highlighted the dependency of air power not just on machines, but on the people who maintain them. Psychological pressure weighed heavily on both factory workers and combat personnel. Factory employees were acutely aware that delays or errors could impact lives overseas, while air crews faced the daily reality of mortality with every mission. Letters from home, wartime propaganda, and a sense of patriotic duty helped sustain morale, yet the emotional toll was undeniable. The war demanded both technical skill and mental resilience, with each success tempered by the constant shadow of loss. The contribution of women and minorities reshaped social dynamics on the home front. Women in factories proved their capabilities in skilled labor previously reserved for men, challenging gender norms and societal expectations. African Americans and other minorities, often facing discrimination, demonstrated exceptional skill and dedication, advancing both industrial output and social progress. Their labor was indispensable, and their perseverance under adversity underscored the collective human effort behind mass-produced aircraft. Families and communities also bore the burden of war. Workers juggled home responsibilities with exhausting shifts in factories, while communities adapted to shortages, rationing, and wartime disruptions. Civilians participated in scrap drives, bond campaigns, and volunteer work, recognizing that their contributions were part of the larger war effort. This interconnected web of effort, at home and abroad, illustrated that the cost of aerial supremacy extended far beyond the cockpit or the assembly line. Despite the hardships, there was a profound sense of purpose. Workers, pilots, and support personnel were united by the knowledge that their efforts were pivotal to winning the war. Each completed aircraft, each successful mission, represented a tangible contribution to defeating the Axis powers. The industrial and human systems of production and operation became inseparable, illustrating that technological achievement alone could not secure victory. It required the courage, perseverance, and ingenuity of millions of Americans. By the end of 1944, the United States had demonstrated that mass production, innovation, and human endurance could be synchronized on an unprecedented scale. Aircraft dominated skies not simply because of engineering, but because human effort had transformed raw materials and machinery into instruments of strategic power. The human cost behind these machines was immense, yet it underscored the extraordinary commitment and resilience that enabled the United States to sustain global air operations and achieve decisive victories. By 1945, the U.S. aircraft industry had evolved into a seamless and adaptive network, where production, supply, and operational feedback formed a continuous cycle of improvement. Factories not only produced planes in unprecedented numbers, but also refined designs based on real-time combat experience. Engineers and production managers communicated directly with field units to understand mechanical issues, mission challenges, and performance limitations. This feedback loop allowed the integration of incremental innovations, stronger engines, improved armament, reinforced fuselages, without interrupting the flow of mass production, ensuring that American aircraft remained at the cutting edge. Supply chains became a strategic asset. Thousands of suppliers across the country manufactured engines, propellers, electronics, and weapon systems. Railroads, trucks, and ports ensured that materials moved efficiently from mines and factories to assembly lines. Forward airfields relied on standardized components for repairs and replacements, minimizing downtime. The sheer scale of this operation demanded meticulous planning and coordination, yet it was executed with extraordinary precision. Every part, from the smallest rivet to a full engine assembly, was critical in sustaining continuous operations across multiple theaters of war. Technological adaptability was equally important. As enemy aircraft evolved, so too did American designs. Production lines were modified to accommodate new models or improved versions of existing planes, and innovations in aerodynamics, electronics, and armament were rapidly incorporated. Factories became dynamic hubs of problem-solving, where engineers, technicians, and line workers collaborated to implement improvements while maintaining output. This ability to innovate without sacrificing scale gave the U.S. a decisive advantage, ensuring that quantity did not compromise quality. Maintenance and repair infrastructure mirrored this adaptability. Spare parts were mass-produced to standard specifications, allowing rapid replacement in field conditions. Engines could be swapped, wings repaired, and avionics recalibrated using factory-fresh components. This system created resilience, ensuring that aircraft could remain operational even after sustaining damage. In effect, the industrial network became an extension of the battlefield, enabling the sustained application of air power on a global scale. The coordination of industrial output and military strategy was unprecedented. Production priorities were adjusted based on theater-specific needs, ensuring that long-range bombers reached the Pacific, while fighters were delivered to European fronts where escort and tactical support were critical. This strategic allocation of resources maximized the effectiveness of American air power, demonstrating that mass production could be more than a numerical advantage. It could directly shape the course of war. Human ingenuity remained central to sustaining supremacy. Factory workers, engineers, mechanics, and pilots contributed expertise, creativity, and resilience. Women and minorities filled roles critical to both production and maintenance, often under challenging conditions. The emotional and physical dedication of these individuals ensured that technological sophistication translated into operational reality. Their labor, often unsung, was the backbone of America's aerial dominance. Continuous innovation extended beyond the aircraft themselves. Improvements in training programs, logistics, and maintenance procedures increased efficiency and effectiveness across the entire system. The integration of technology, human skill, and strategic planning transformed the U.S. aircraft industry into a force multiplier, capable of sustaining complex, global operations while adapting to the evolving demands of war. By the closing months of the conflict, the United States had achieved a level of industrial and operational sophistication unmatched in history. Aircraft dominated skies worldwide not only because of their design, but because of the extraordinary coordination of production, logistics, and human effort. This synergy ensured sustained supremacy, turning raw materials and ingenuity into a decisive instrument of war. The legacy of this achievement would resonate far beyond 1945, demonstrating the power of organized innovation and collective effort on an unprecedented scale. As 1945 approached, the results of America's monumental industrial effort were undeniable. The skies over Europe and the Pacific were filled with aircraft produced in staggering numbers, each one the culmination of innovation, labor, and logistics operating at historic scale. Strategic bombing campaigns had crippled enemy infrastructure, fighter escorts dominated contested airspace, and the relentless pace of deployment ensured that Allied air forces could sustain operations across continents. The mass-produced machines had become extensions of national power, embodying both technological achievement and human endeavor. The human dimension of victory remained central. Pilots who had trained on newly assembled planes executed missions with precision and courage, often at tremendous personal risk. Maintenance crews and mechanics worked tirelessly to keep aircraft operational, repairing damage from combat or environmental stress. Factory workers, many of whom had never left their hometowns, could witness the tangible results of their labor as aircraft left production lines and took to the skies. Every success in the air was inseparable from the thousands of hands, minds, and hearts that had contributed on the ground. Mass production had not only provided quantity, but also enabled rapid adaptation to changing battlefield conditions. As enemy technology evolved, American aircraft could be upgraded with new engines, armament, and avionics, often during the production process itself. This agility ensured that technological superiority was maintained even as the pace of war intensified. Factories became arenas of innovation, where engineers, technicians, and workers collaborated to transform design improvements into operational aircraft without missing a beat. The logistical networks supporting these operations were equally remarkable. Spare parts, fuel, ordnance, and replacement aircraft moved seamlessly from factories to airfields, ensuring sustained operational readiness. Forward bases were supplied with everything needed to repair and deploy planes quickly, turning industrial production into immediate combat capability. The integration of production, logistics, and tactical deployment created a system that could endure the attrition of prolonged conflict, giving the Allies a decisive strategic edge. The war effort also reshaped American society. Women, minorities, and previously marginalized groups had demonstrated their essential role in industry and military support. Their contributions challenged societal norms and laid the foundation for post-war social change, highlighting that victory was achieved not solely through machinery, but through the mobilization of an entire population. The industrial and social mobilization required to dominate the skies left a lasting imprint on the nation's identity and capabilities. American air power by 1945 symbolized a fusion of ingenuity, labor, and determination. The ability to design, mass-produce, and deploy advanced aircraft on a global scale reflected both the technological prowess and organizational skill of the United States. Bombers and fighters were more than weapons. They were instruments of strategy, endurance, and innovation, demonstrating the transformative potential of coordinated industrial effort. Each plane in the sky carried with it a story of collective human achievement, from the factory floor to the cockpit. The lessons of this achievement extended far beyond the immediate conflict. The techniques, technologies, and organizational methods developed to produce and deploy aircraft at scale informed post-war aviation, aerospace, and industrial strategy. The integration of design innovation, mass production, logistical excellence, and human effort set a precedent for future conflicts and for peacetime technological advancement. The legacy of this effort would continue to shape the possibilities of human achievement for decades to come. Ultimately, the skies over Europe and the Pacific in 1944 to 1945 were a testament to the extraordinary capacity of a nation united in purpose. Mass production, innovation, and human resilience converged to create air supremacy, securing victory and demonstrating that industrial might, when combined with skill, courage, and ingenuity, could achieve what once seemed impossible. The story of American aircraft in World War II stands as a lasting reminder that the power of the human spirit, amplified by technology and organization, can reshape the course of history.